This is fundamental problem 10 from chapter 18. The 30 kilogram rod is released from rest when theta is equal to 0 degrees. Determine the angular velocity of the rod when theta is equal to 90 degrees. The spring is unstretched when theta is equal to 0 degrees. So initially, the rod is horizontal. The rod has a length of 1.5 meters, and this distance here is 2 meters. So that means when the spring is unstretched, its length is 0.5. And when the rod is at an angle of 90 degrees, we can use the Pythagorean theorem to find the length of the spring. So since this is the hypotenuse of our right triangle here, the length of the spring is 2 meters squared plus 1.5 meters squared. All right, so we are going to use the work-energy relationship to solve this problem. So that's equation 1818. Initially, the spring is at rest, so T1 is equal to 0. And for potential energy, we have both elastic potential energy and gravitational potential energy. The elastic potential energy is 1/2 ks squared. And for gravitational potential energy, I can say the initial gravitational potential energy is 0. I can say the final gravitational potential energy is 0, or I can just look at the change in gravitational potential energy. I have the work done by non-conservative forces, which in this section, the work done by non-conservative forces is always equal to 0, since this is in the conservation of energy section. We have final kinetic energy, and we have final potential energy. And for final kinetic energy, we can use equation 18:6, or we can use equation 18:7. So initially, the spring is unstretched. If the spring is unstretched, S is equal to 0. Remember, S is the difference between the current length of the spring and the rest length of the spring. Since the current length is equal to the rest length initially, the initial elastic potential energy, let's call that VE1, is equal to 0. Then let's just do the change in gravitational potential energy. And we're starting off when the angle is 0. We're ending when the angle is 9. So if you look at the mass center of the rod, initially it's here. Finally, it's here. Since the mass center is in the middle of the rod, the change in height is half of the length of the rod. So that's 0.75. And the height decreased. So the change in gravitational potential energy is negative. So that's M times G times 0.75 meters for the change in gravitational potential energy. The work done by non-conservative forces is 0. And the final kinetic energy, let's use equation 18:7 for that. The instantaneous center of 0 velocity, well, you can say it's here, or you can use equation 18:7 with the moment of inertia about pin O instead of the instantaneous center, but pin O is the instantaneous center of 0 velocity. So this is T2, that's 1/2, let's call it IO. You can call it the moment of inertia about the instantaneous center if you want. It's the same thing. Since this is at one end of the rod, we go to the table in the back of the book. We look for the moment of inertia for the rod about one end, and that is 1/3 ml squared. So this is 1/2 times the moment of inertia about one end, which is 1/3 ml squared. L is 1.5, that's the length of the rod. And then we have omega squared. Okay, we already took care of the final gravitational potential energy, so now we just need the final elastic potential energy. And for elastic potential energy, it's 1/2 ks squared, where S is the difference between the current length and the rest length. The rest length is 0.5. The current length is what we have here. So this is 1/2 times k times s squared, where s is the square root of 2 squared plus 1.5 squared minus 0.5, and it's s squared. So this is s in parentheses, it's this minus this, and then we square it. Okay, and then putting that all together using equation 18-18, I have 0 plus 0. If I do the change in gravitational potential energy, I'd bring the initial gravitational potential energy over to the other side. So this is 0 plus 0 plus 0 for the work done by non-conservative forces is equal to T2, which is 1/2 times 1/3 times m times 1.5 squared times omega squared, plus the change in gravitational potential energy, which is minus mg times 0.75, plus the final elastic potential energy, which is 1/2 times k times 2 squared plus 1.5 squared minus 0.5 squared. Okay, now we are looking for the final angular velocity. I know what the mass is, I know what k is, so if I put in 30 kilograms for the mass and 80 newtons per meter for k, then I can solve for omega. So I have, let's see, omega is in this term here, so I can bring these two terms over to the other side. And I have 1/6 m is equal to 30. 1.5 squared times omega squared is equal to, bringing this over to the other side, that would be 30 times 9.81 times 0.75, and then bring this over to the other side also, and it would be negative, and k is equal to 80, so that's half of 80, which is 40. So that's 1/2 k times this, which is 4 minus 1.5 squared minus 0.5. Okay, and then solve for omega. And this 1/6 times 30 times 1.5 squared is 11.25. We can divide both sides by that, then take the square root. And what we have here, this is negative 160, and this is 220.75. And so we get, for our final angular velocity, 2.32 radians per second. That concludes fundamental problem 10.